When watching this video, you might ask a friend, what kind of bird is this? When we communicate our conclusion to others, we point out parts of the bird and explain that they are similar to the usual or prototypical aspects of that bird species. Here, the black crown, yellow back, black and white wing bars, and yellow belly all support the conclusion that this bird is an American goldfinch. Our deep learning classifier is able to reason in a similar way, then present that reasoning to an end user. Beyond earlier work in interpretability by Chen et al., our new deformable ProtoPNet is able to consider context and explicitly account for pose and scale variation to more closely mirror human reasoning. This method achieves state-of-the-art accuracy among interpretable models, is able to learn prototypes and prototypical parts using only image-level labels, and works with most neural network architectures. While other methods of interpretability exist, ours is one of the few that guarantees that the explanation given shows the actual underlying decision-making process of the model. During training, our model learns a set of prototypes, each composed of multiple parts that may change their relative spatial positions. When classifying a bird, the network compares a new image against each prototype learned during training. For each new image, a deformable ProtoPNet predicts how best to deform its prototype at each location in the image, providing logical explanations even with the presence of variations in pose and scale. So, how does this work? We use the convolutional layers of a standard CNN backbone to create a latent representation of each image. We normalize each spatial location of the latent representation to a fixed length, forcing these objects to reside on a latent hypersphere. These normalized latent vectors are taken as input to a secondary offset prediction network, which produces a field of offsets used to deform prototypes. When comparing an entire prototype to an input, we stack each part of the prototype to create a higher dimensional vector that resides on a higher dimensional hypersphere. We then stack and normalize each deformed part of the input for every spatial location in the input. A deformable prototype is considered similar to a section of an input image when the angle between these stacked higher dimensional vectors is small. It is worth noting that allowing prototypes to deform spatially creates a complication. When a prototype deforms, it almost always does so with fractional offsets, meaning it will compare each prototypical part to a fractional location in the input. If we use bilinear interpolation to get the value of our input at that location, the resulting vector will not reside on the latent hypersphere. To address this issue, we introduce norm-preserving interpolation, which guarantees that the interpolated vector will still reside on the desired latent hypersphere, preserving our geometric interpretation of the latent space and allowing us to use cosine similarity on interpolated features. We further shape the latent space using subtractive angular margin loss, which artificially decreases this angle between each input and prototype of the wrong class during training. This forces the network to increase the angle separating prototypes and inputs of different classes. By combining this with the explicit separation and cluster loss terms introduced by Chen et al., we create a latent space in which prototypes and inputs of a class cluster together, and each class cluster is separated from the others. We found experimentally that introducing these loss terms, along with orthogonality loss, in tandem with deformable prototypes, results in a model that produces quality explanations with a high degree of flexibility to changes in spatial pose. We found that deformable prototypes often have a high degree of semantic correspondence to the input images considered most similar to them. Similarly, we found that the most highly activated prototypes for a given image show a high degree of semantic correspondence to the image. Across 7 standard CNN architectures, a deformable ProtoPNet achieves superior accuracy to both the baseline model and to a corresponding ProtoPNet model on the CUB 200 2011 dataset, and that a deformable ProtoPNet achieves similar or superior accuracy to the baseline model across 3 standard architectures on the Stanford Dogs dataset. Further, we found that deformable ProtoPNet can achieve state-of-the-art image classification accuracy among interpretable models on both CUB 200 2011 and on Stanford Dogs while providing superior interpretability. For more information, please see our paper. Thank you.